Everybody. This is Aditya Kalyani. Today I'll be speaking about the description and design of the LDO structure with different configurations. Like as on the screen, you can see the schematic of the LDO that has been designed. Basically, getting into that before, let us see what is an LDO. An LDO consists of a voltage reference that is given here, VREF. It's coming from the source VREF here. An error amplifier. This structure is an error amplifier. Voltage feedback divider. This is the voltage feedback divider, and moreover, a pass transistor. This structure is a pass transistor as added. So basically, there are the two types of LDOs. One of them majorly both of them majorly are because of the pass transistors. One of the pass transistors in one of the configurations is an NMOS, and in the other is a PMOS. LDO typically it includes an error amplifier that compares the output voltage with the reference voltage. So this is the output voltage, and this output voltage is compared with the reference voltage. To ensure negative feedback, we see that VFD, the feedback loop, is given to the positive terminal of the error amplifier. Moreover, the pass transistor is a key component that controls the flow of current from the input to the output. Here, the input is generally the VDD, the supply voltage, which varies. Next, a feedback network that is often built using a set of resistors. Here, as seen, a feedback resistor that provides a portion of output voltage to the error amplifier for comparison. So the design of the LDO is based on the specifications provided. Mainly, as said, there are two types of LDOs that are designed based on the dropout voltage and the PSRR specifications. If we are using a NMOS pass transistor here, then that is generally because NMOS pass transistor has high PSRR rejection, like power supply ratio rejection. Hence, if the constraints speak for a high PSRR, generally PSRR is in negative in values. So if you need higher PSRR, that is more negative values, then an NMOS is chosen as it rejects the supply voltage that whatever is coming, VGS remains constant. But whereas in that case, we see that at least one voltage drop between VGS, between gate to source voltage, is always one VTH of voltage is always needed to keep the NMOS turned on. Hence, we see that LDO basically needs at least a drop of voltage of threshold if we are using an NMOS. Generally speaking, some of the industrial applications ask for a low voltage dropout regulator in the sense of around 200 to 300 millivolts. And if we have that constraints, then it becomes very difficult for us to use NMOS as NMOS voltages, NMOS devices, at least for a longer view. And like the corresponding design is in 65 nanometers. The threshold voltage is around 450 to 500 nanometers. So in that case, we would not be able to use an NMOS. Whereas in case of PMOS, as this circuit is built using a PMOS pass transistor, works for a lower dropout voltages as well. So, but yes, we have to have constraints on PSRR then, like we have to compromise upon the PSRR, but it is still possible, as will be shown, that you can achieve a very good PSRR using a PMOS pass transistor. So generally, I will not go into the details of how the single stage amplifier is designed, but let's go into the details of how this PMOS pass transistor is designed. So this is a normal single stage amplifier. So this is a current mirror. 100 microamperes of current is pumped through the current mirror, and it is then mirrored using a tail current source and using a mirroring circuit. And then basic architecture of a single stage amplifier is built over that. We see that this system, when including a pass transistor, will become a two-pole system. Hence, it is very essential for us to have a good phase margin. Hence, we have to use Miller compensation. So this structure, the R and C here shown, are basically used to construct, is used for Miller compensation. How do we achieve Miller compensation? Miller compensation basically works upon pole splitting. It pulls the dominant pole to the leftmost side and the non-dominant pole to the right-hand side of the body block. So this ensures that the gain bandwidth is generally reached before the second pole. Hence, we get a good phase margin. How do we design this PMOS pass transistor? What are the constraints on designing the PMOS pass transistor? First of all, the main and major constraint is the dropout voltage. The current scenario is at least takes into consideration for a dropout voltage of 200 millivolts. What happens is for as a voltage is required, the PMOS transistor pulls the required amount of current. That required amount of current is passed through the feedback. Hence, a voltage is established at the feedback network. Once the voltage is established at the feedback network, then the output voltage can be controlled. Using this feedback network can also control the output voltage that is necessary. Also, this is as an industry spec. I'm using a 100 pico of load capacitor, and our load is the variable load resistance that is used to ensure different currents through it during simulations. So this is the basic architecture. Okay, this is a current probe. This current probe is generally used to check for various kind of simulations, XF simulations that is used for PSRR and stability simulations. So this is a 100 microampere current source. I'm pulling out a tail current of around 80 to 70, 75 to 80 microamperes because we had a constraint of maximum of quiescent current to be 100 microamperes. So how do we define quiescent current? Quiescent current in this circuit is the maximum amount of current that does not go through the load. So where all are the paths for quiescent current? One is through this tail and the other is through this feedback. So the circuit is designed to ensure that it has a quiescent current of less than 100 microamperes across all temperature ranges and across all corners for all voltages. So this is the basic architecture of the LDO. Here, N bulk is the connection that is ground. Generally, we separately connect the bulk of all the NMOSs together to ensure that we have taken body effect into consideration. ESS is the normal ground, VDD is the supply, and VREF currently taken ideal is the reference voltage. So this is about the architecture of the LDO. Speaking more about compensation, we are using a single digit picofarad compensation, around 6 picofarad capacitance and 1.5K resistance for Miller compensation to achieve a phase margin of greater than 45 degrees. So that is the basic constraint for phase margin. So heading into simulations. So currently, let me show up the simulation portfolio. Yeah, our load is taken as 750. I have designed this to get an output voltage of 1.5 volts. So 1.5 divided by 750 ohms gives us a load current of 2 milliamperes. So the circuit currently pumps a load current of 2 milliamperes. Reference voltage is taken to be 900 millivolts. The reference voltages can be other voltage of reference can also be taken. The reference voltage is generally designed using a BGR circuit. So currently we're not going into the details of the BGR. So the ideal reference voltage of 900 millivolts is taken. Let me show up some initial simulations. This loads a basic simulation. I have run the simulation from 0 to 200 micro. Let's go with the load current of 2 microamperes, maximum supply voltage of 3.3 volts, and I'm plotting out VDD, Vout, output voltage, and let me plot the output current as well. So let me just run the simulation. Yeah, so here we see the graphs. This is a very high fluctuation, but it's less than microvolts of range, so that should not affect us at all. Let me split it. Yeah, as you see, this is in 1.4499 volts, and this is 1.49911. So this corresponding means that it's constant. The fluctuations is in microvolts range. So the output is then the input voltage of 3.3, output current of around 2 milliamperes, and output voltage of 1.499. So it's like 1.5 volt. We're able to see a simulation of output voltage for 1.5 volt. Speaking more of it, let's go into simulations. Okay, speaking more of the simulations, I have taken a normal transient simulation for 200 microseconds. The duration can be controlled, and the output voltage, supply voltage, and current through the resistor, the output resistance. So the load current is plotted. So what else? Let's go into PSRR simulations. I've already run the simulation and saved, so I'll be opening those parts. To do output simulation, okay, let's take 3.3 volts. So what is XF simulation? XF simulation generally takes for PSRR. So I'll just open the simulation portal once. So it's XF, and what is your start and stop frequency range, and what is your positive node where the XF signal is given. So let me show you in the schematic. Here we go. The VDD supply. Once we give an ideal voltage of VDD, we also specify an XF voltage, XF magnitude of 1 millivolt for XF simulation. So XF simulation gives us a run for the PSRR values. So yes, let's go into the simulations. I have plotted this as the supply. This is the voltage source, and this gives us this is equation for PSRR. It's a 20 dB plot for XF values, and I just run the simulations. Well, we can see PSRR. Yeah, here we go. So this is really good. We are seeing a maximum PSRR of negative 63. I think that's a pretty good value. This constraints while I was designing this was greater than minus 40 dB for 1 megahertz of signal. And what do we see? We see around minus 75 dB. That's pretty good. The more negative PSRR, the better is the circuit. So any fluctuations in input aren't seen actually at output. Greater negative value of PSRR, greater is the rejection. It's power supply rejection ratio. So here, this is the PSRR plot. We see that the PSRR is completely negative across all the frequency ranges with a minimum value of around 60, minus 60, greater than minus 60 dB. So that's a very good solution. So this is about the PSRR of the circuit. Maybe let's move into the stability of the circuit as well. So I have simulations for that as well. Let's go. So this is the stability. So let me run it at 750. So maximum output current. And how do we test stability? To test stability, we have a simulation called as STB analysis. How does STB analysis work? So can you pop it in? Yeah, this is STB analysis. Start frequency, stop frequency, and a probe. As told before, the probe is here. This probe IPRBO0 is used for STB analysis. So this breaks the loop at the feedback and then checks for the stability of the system. As the input increases, how does the output behave? So this is STB, then you take 3.3 maximum current, a transient simulation, and run the system. So here we don't get a plot. So how do we evaluate as progress? We go to results, direct plot, main form, and then STB analysis. Here we see STB and a phase margin. Oh, that's a very good phase margin. Loop gain, let's plot it. Here we get plot for loop gain. So yeah, that's greater than 40 dB. And we have a phase margin that's pretty greater than 60 degrees. So that's a very acceptable value. Just going, I have a DC gain of around minus 40, like DC gain of 40 dB. 40 dB is like around 1000 gain, 40 dB. That's a pretty good range of gain for an LDO. So this is the basics of LDO simulations. Here the complete system is simulated using, as specifying again, using a PMOS pass transistor. We can always go with an NMOS pass transistor based on the required constraints. This is a circuit that is generally designed for a voltage range of 2.2 to 3.3 volts, and it meets all the specifications. If I just go once through the Google form, and if I might be able to show you how the specifications are designed. Okay, I don't have the specs. I might have to reopen the specs. So currently, yes, this is the specs range that it was designed for. So this is the basics of LDO. Recapitulating again, it's a basic structure that consists of error amplifier followed by a PMOS transistor and a feedback loop. The feedback loop is done to ensure output is fed back into the amplifier, checked by the error amplifier. If the output rises due to negative feedback, the output is settled back. This takes 100 microampere of load current and 100 picofarads of output capacitor and load capacitor, and is designed for currents ranging from 100 microamperes to 2 milliamperes. Can be designed further for a greater range as well, easily. So this is the basic architecture of the LDO. Thank you. Any queries, please let me know. Thank you.